Alright, welcome to our next major unit in physics. We are going to start our unit on forces, and to start that off, we're going to define forces, but also we need to talk about a really famous person, Sir Isaac Newton, and his three laws. So let's start with a basic definition. Forces are either a push, alright, so you're pushing on something, or a pull, you are pulling on something. Then my formatting got messed up, but what is supposed to be written down here is the units for force are newtons, aptly named after Sir Isaac Newton, which can be abbreviated with a capital N. Well, let's keep going. Let's continue. Mr. Newton. So Sir Isaac Newton kind of set the framework for our complete understanding of forces. He set up three laws, the first of which is Newton's first law, which has three major points to it. First one is an object in motion stays in motion. Alright? So if an object is moving, it wants to keep moving. Second part is an object at rest stays at rest. So if an object's not moving, it doesn't want to start moving, and it's not going to start moving out of nowhere. And then the third part, and this is true unless acted upon by an outside force. Alright? So objects in motion keep going unless an outside force stops them. Objects at rest stay at rest unless some sort of force makes them start moving. Okay? Another thing to note about this is a change in direction indicates a change in motion. Alright, so objects that are in motion in a certain direction have to stay in that direction unless they are acted upon by an outside force. Alright, so if you think about my pen mark here, I'm moving towards the right, alright, and in order for me to stop doing this, it requires a very specific action, thought on my part, movement by my hand, the line has to stop, and then I have to start drawing in the other direction. Okay, so a change in direction must be caused by a force. Another kind of extra part to Newton's first law. Now, Newton's second law, very simply stated, is F equals ma. Alright, so we'll get into this later, but for now, make sure you just know that Newton's second law is this equation. Force equals mass times acceleration. Alright? We talked earlier about the fact that force's units are newtons. Because of this equation, the units for mass are kilograms. The units for acceleration are meters per second squared. So m times a is going to be kilograms times meters per second squared. So this is another way of noting the units for a force. Okay, so more often than not, we will use newtons, but this does come in handy for understanding how you get meters per second squared back out of a force, things like that. And Newton's third law is for every action, there's an equal and opposite reaction. Okay, so if you think about you standing on the grass, all right? Seems like nothing's going on, but gravity is always pulling you closer to the center of the earth, except you don't fall through, right? Because there's an equal and opposite reaction of the earth pushing you back up to make sure that you stay where you are. All right? Another idea of this is, say, a brick wall here. If you push on the brick wall, you don't actually go through it. I mean, you have to push really hard to go through it. But say you're just up against the wall in the classroom and you're just pushing on the wall. You're pushing on the wall, but nothing's happening. That is because the wall is pushing back at you with an equal and opposite reaction. We'll talk about this in more detail in the future. Our primary focus today is Newton's first law. So, repeat on that. It's Newton's first law, an object in motion stays in motion. Okay, so if it's moving, it wants to stay moving. An object at rest wants to stay at rest. The only reason this changes is because there is an outside force causing the motion to stop or causing the motion to start. Okay? A very key, important word related to Newton's first law is the word of inertia. Inertia is defined as the tendency for an object to resist a change in motion. So inertia resists change in motion. All right, so think about things that are hard to move. All right, stuff that's really hard to stop, or things that are really hard to get going. Odds are you're thinking about things that are heavy or big. All right, things that have a lot of mass. All right, so, and that is entirely why inertia is related to mass. So the amount of inertia is proportional to the mass of the object. So a bigger object has more mass. So that object also has more inertia. All right, so objects with more mass have more inertia and are going to resist changes more. All right, you know, think about an elephant. Could you pick up and move an elephant? I'm hoping you're saying no. Now think about a mouse, a lot tinier. Could you pick up and move a mouse? All right, big, huge amount of mass, really hard to get it moving. If that elephant doesn't want to go anywhere, it's not going to go anywhere. The mouse, on the other hand, really tiny. If you want it to go somewhere, you can make it go somewhere. Same idea with objects in motion. All right, what would you rather get hit by if you were, say, your car was stranded and there's something barreling down at you? A tricycle or a semi? All right, tricycle, probably not going to hurt you very much. A semi is not going to be affected by you at all, and it's just going to go blow right all over you. Okay, so big things, keep moving. Little things, a lot easier to stop them. Because of this direct correlation between inertia and resistance to motion, Newton's first law is often also referred to as the law of inertia. Okay, so second name for Newton's first law is also the law of inertia. So the rest of this is, let's see, if you scroll down to the end, there is a little bit of practice, but here are just some videos that are examples of Newton's first law, so you can actually see some of it in action. These are both examples of things that are at rest and want to stay at rest. Okay, so if an object isn't moving, it's going to try to keep not moving. You have to apply a force to get it going. So first one is the tablecloth trick. We had a little bit of trouble. Alright, so tablecloth trick, the plates don't want to move. Alright, so you have to be very skilled at getting the tablecloth out of there, otherwise it's just going to get stuck underneath the plates that don't want to move. Alright, here's another one.
Key is, you got to hit it quick and short, and you got to hit the pie tan quick and short. If that happens, in theory, the pie tan will hit the paper towel roll out of the way, but the egg has more mass. Hopefully it wants to stay at rest, and we'll see it plunge into the water and go swimming. That's the goal. Try it. Oh my goodness, I'm nervous. Now you got to hit it pretty forceful, but not go too far. Okay. Okay. Nice!
Okay, so like the teacher was saying, the pie tin and the paper towel roll have very little mass. It's easy to get those moving, and as long as you just hit that and you don't actually hit the egg stays at rest. But once its support, once the towel roll disappears, the egg has to fall. But the egg did not move sideways. Okay? Here are a couple of examples of objects in motion that want to stay in motion. Okay. I preface this by saying, do not try this at home.
Fly back.
So, he slammed on his bike brakes, except he was still in motion. So while the front tire was not moving, the back tires still wanted to go, and so did the boy, which is why he kept going forward. And one last one. So, this one's kind of an example of both. If you notice, it's hard to get the cow going at first because the cow has a lot of mass and a lot of inertia. But once you get the cow spinning and you let go, it just keeps flying until, of course, the ground applies another force and stops the cow. This isn't a whiteboard thing, but just try these. See if you know what the answers are, and I'll give them to you in a second. But first one, true or false, an object with more mass will have less inertia than an object with less mass. So is that a true statement or is that a false statement? And then if a ball is rolling in an endless vacuum, meaning absolutely no friction, the most common force that stops things is friction. So let's say we get rid of it. Will the object ever stop? And then, will the same ball as above ever change direction? Then the last one, if an object changes speed, such as coming to a stop, what caused this? So see if you can figure out what those answers are, and I will tell you the next slide. So, on the next slide, here's the answers. That was false. Mass and inertia are proportional, which means if you have a lot of one, you have a lot of the other. Okay, as mass goes up, so does inertia. And then if a ball is rolling in an endless vacuum, meaning no friction, will it ever stop? The answer is no. The reason why things rolling on Earth stop is because the floor has friction, and friction is a type of force. Same thing for number 3. Will the ball above ever change direction? No. There has to be a force acting on it. And in a vacuum, as long as there's nothing else in there, there's no forces to do anything to the ball, so it's just going to keep rolling and rolling forever off into oblivion. Okay? And then if an object changes speed, such as coming to a stop, what caused this? Any change in motion is caused by a force. Okay? So make sure you do the online assignment, and I will see you in class tomorrow.